Good day. I am Vyasa from Intel Folsom, California, attending the conference in person today. With me are my co-authors, Vaibhav and Fylur, also from Intel Folsom. Our topic for today, exploring ML to assign debug priorities to improve the design quality. This is a step towards trying to address the huge amounts of money spent by companies due to missed tape out or stepping or buggy chips in production, in order to find design bugs fast enough. With the increasing complexity of modern designs, design flaws increasingly escape to silicon and later stages. Discovering design bugs after the product release may lead to expensive product recalls. Hence, the typical goal has been to find as many design bugs as possible before shipping. For example, finding a design bug at the IP verification stage is way more costly than finding it at the coding stage. Current studies suggest that this is due to the increase in resources required to identify and bucketize bugs after coding. A typical design debugging flow, we have the following phases: regression, failure bucketization, assignment, debug, fix, and fix validation phase. Goal of regression is to ensure the design performs as expected by launching and executing test lists. Literature survey suggests that failure bucketization is a fast-growing regression pain, occupying up to 30% of the debugging effort. Failure bucketization and assignment happens after regression is complete, and it precedes the detailed debugging stage. Basically, a high-level analysis is done to understand the nature of these failures, triage, and eventually assign them to relevant engineers for detailed analysis. Constitutes an important pre-processing debugging step, also referred to as the failure bucketization. Despite the growing regression pain in bucketization, typically it is handled by high-level debugging, such as grouping similar errors together. And these inaccuracies reflect into adding additional debugging overhead in the detailed analysis stage. Hence, our research work explores the prioritization of regression failures in verification using machine learning. So if you look at this flow, the goal is to apply ML these two stages. One of the main objectives of the proposed solution is to identify whether a particular failure in a regression indicates a possible RTL design issue based on the historical data captured for previous failures using ML. The captured error messages in the regression logs will be the input to the ML model. And this ML model classifies an input message as a possible design or a non-design issue based on learning from the past failures. And non-design here refers to examples such as test bench issues or BFM issues, among others. The ML model inputs and outputs are error signatures and type of bug respectively. Hence, the ML problem in this context is a binary classification problem with text data as input. Once the ML problem has been formulated, data wrangling is done so that cleaned data is fed as input to the ML model. Data wrangling here refers to gathering, assessing, and cleaning. The training and testing of this ML model comprise the next steps. That's me at the end of my talk. So I will now hand over to my colleague, Vaibhav.
Thank you, Vyasa. So now we discussed the machine learning and debug automation flow used in this paper. So we already discussed in the previous slide that the problem formulated as a text classification problem with two classes, which is basically binary classification. So the next step of the solution is to collect data which will be used to train the machine learning model. We have a database of past failures which have been debugged and root caused to either a design or a non-design bug. A Python-based SQL API is used to collect data from past failures. As real-world data generally contains a lot of noise, data assessment and cleaning follows data collection. Once clean data is available, it is used to train the machine learning model and tune various hyperparameters to produce the best classification performance. After finalizing the hyperparameters for the machine learning model, a test set is fed as input to the machine learning model and the classification performance is analyzed. Now, if the performance is not good enough, we revisit the steps of data collection, assessment, cleaning, and hyperparameter tuning of the machine learning model to improve the performance. Once the performance is satisfactory, the machine learning model is fed with live data from regression failures and outputs the design probability for each failing test. This information of design bug probability is stored in a cloud database along with other error details like the error message, the RTL file, the RTL module, the time of the error, and so on. Now, if the design bug probability is above a certain threshold, the simulation for that failing test is relaunched with waveform dumps. The relevant debugger is notified once the waveform dump is available, along with the instructions to open the waveform and update the database with debug details once the failure is root caused. All the steps of this automation are implemented through a Python script, and this easily integrates with the machine learning code, which is also implemented using Python-based libraries. Now, the data wrangling process consists of several steps and consumes a significant amount of time and effort in any machine learning based solution. A Python-based SQL API, as mentioned before, is used to collect data from a bug database. Each bug has various details like the bug title, description, the module name, the test name, and so on. The raw error message is extracted from the bug data and some pre-processing steps are applied on it to produce a clean error message, which is then fed as input to the machine learning pipeline. Now we discuss our experimental results, and the bar chart on the left shows the classification performance of different machine learning models on the test set. The different machine learning models tried for the classification problem are logistic regression, support vector machines, decision trees, random forests, and adaptive boosted decision trees. The classification metrics used for measuring the machine learning model performance are precision and recall. The recall for the design class is given more importance because missing a design bug is more costly from the business perspective. The left bar chart shows the design precision and recall for the different machine learning models tried in the paper. From this graph, we can see that random forest classifier achieves the highest design recall of 0.94. However, it has an extremely low non-design recall of 0.28. In comparison, ADA-Boost classifier achieves a design recall of 0.82 and a non-design recall of 0.5. It also has a higher design precision compared to the random forest classifier. So overall, the ADA-Boost classifier is found to have the best classification performance among all machine learning models. Now, the figure on the right shows the confusion matrix for the best machine learning model, which is the ADA-Boost classifier. The x-axis shows the predicted label, and the y-axis shows the true label, which is either design or non-design. And there are 4 quadrants shown in this figure, where the top left quadrant shows the percentage of design hit, which means that the machine learning model is able to predict a design bug accurately approximately 82% of the time, while it misses predicting an actual design bug about 18% of the time. And at the bottom, we see that the machine learning model misses to predict an actual non-design bug around 50% of the time, and it predicts a non-design bug correctly also about 50% of the time. So now we come to the conclusion of our presentation. So the key points to gather at the end are as follows. So the solution proposed in our paper is a good application of machine learning for debug prioritization. This obviously requires proper data collection, the correct kind of data, and extensive data wrangling, which are the main challenges and also consume most of the time and effort in the solution. Then the machine learning model performance also can be improved further by using better data cleaning techniques, better hyperparameter tuning, exploring more machine learning models, etc. And finally, we can also extend this work to solve other similar and related problems in the field of hardware validation. So that was the end of our presentation. Thank you very much for listening.